Okay, morning everyone. I guess we can start now. So this session is mainly about high-performance microservice development in real time. So what I wanted from this discussion today is kind of like you leave this room with something you can take out. It doesn't matter what programming language you use. It doesn't matter if you're coming from data science background or from engineering background. These concepts can be applicable to different domains. So my name is Fawaz Ghali. I am the principal data science architect and head of developer relations at Hazelcast. And for this discussion, what I wanted is give you some kind of idea what real-time applications are and how you can take advantage of the amount of data and process it in real time. So just to get things started, anyone can guess who are these guys on the screen here? Yes, that's correct. So these are the betas. So I came from Liverpool, from the UK, so that's where I am based. And it's kind of like what I wanted to think about this talk is, if you think about it like you want to write a song lyrics, so essentially what kind of ingredients you want to add into your application to do it. Most people assume writing real-time applications is easy task. And if you look at it, it looks like it's a straightforward process. So you start by developing and creating microservice application, and you assume, or someone will assume, that the results will come eventually as expected. But we all know that's not the case. There is always a room for errors, and there is always a room for challenges in this process. So these challenges vary, depends on which part of the development cycle you're working on. So sometimes it's more related to how you package your microservice application. Sometimes it comes to deployment, so how easy it is to deploy an application. Or sometimes what are the features that you're gonna use to scale up or scale down your application, because it's important to look at the amount of data you receive, and you just don't want to just look at the average of that number. You want to make sure your application can handle spikes in your data. So what do we mean by spikes in data? So usually if you could average, like, I don't know, maybe 1,000 transactions per day or per week, it doesn't matter the time frame, maybe you get some kind of events, and these events can actually have some spikes in the process in your application. So for example, if you look at Black Friday events, or maybe Christmas, Easter, so where people shop more online, so this type of events can actually have some kind of spikes, and this is where you want your microservice application to handle these type of spikes. And you also want to be able to scale it down, so you don't basically waste resources for the application. Now also load balancing, so how you can, if you have multiple clusters with multiple nodes, how do you manage load balancing, or where you want to send requests to, and essentially what happens if a node fails, how you're going to move the data and the process from one node to another node. And in real time, it becomes the question how you can also monitor your microservice application. So what you want is kind of like to have a management view, which I will show you how you can do it in real time. And this management view allows you to essentially check your memory, for example, memory usage, check your nodes, see what jobs you're running in real time, and if you want, for example, to stop or pause one of these jobs, and you can also track resources. So that being said, hopefully now you can understand the difficulty in creating a microservice application in real time at high performance. So I mentioned real time a couple of times now. You might be asking, what is real time? What do we talk about when we mention real time? And real time essentially means different things for different people. So it's not the same. It depends on which applications you're developing, and essentially also depends on the use case, business use case. So some applications might mean like a couple of hours. That's what real time is. Could be a couple of days or maybe minutes. So I wanted to ask you a question here just to get everyone up to speed. So anyone can guess how long it takes for an eye to blink? So seconds or less or more? Less, exactly. So it takes about 1/3 of a second. So this is pretty fast. There is no way for a human eye to track these type of actions. And even if you want to write an application to track these type of actions, it becomes really hard to manage it when you want to scale it as well. Clap fans, for example, takes 1/10 of seconds. Also, like digital SLRs and so on. So this type of application, you see it everywhere. So it doesn't matter if you're using this in your work or not. You might be using it as end user, so it could be in finance, banks, or it could be related to IoT devices, and could be related to hospitals, medical use, sports, for example. So anyone follows sports knows that there is elements in real-time stream processing in it, and obviously AI and machine learning. So I'm going to touch about these topics in this talk, but because this is like kind of like a development. So the demo I'm going to use today is to allow you to track traces, to see how you can develop a microservice application and track traces. And essentially what we wanted is to provide some kind of analytics on top of it. So the analytics in this case could be related to defining trends, for example. How do you define a trend? Maybe could be related to, providing some kind of alerts. So usually if you have application, you have some logging system attached to it. And if you want to track these log messages in real time and predict what's going to happen next to your application, you want infrastructure to allow you to do so. And the secret sauce for what we're talking about or describing today for high performance is to combine between two different types of data. So we have new data coming in this moment, in this real time, and we have the historical data. So usually historical data stored somewhere on hard disk or hard drive, or maybe in database and so on. So what you wanted is kind of like having a platform which allows you to do this combination between real-time data and historical data. So why do you need historical data if we're talking about real-time applications? Simply because you want to provide some kind of context. So your application essentially, and when it handles the real-time data, it needs some kind of historical data to provide context for the events you're receiving. Obviously, these two different types of data happen to be coming at different speed, obviously new or faster. So if you store, for example, your data somewhere on hard disk, it becomes slower to process. So you want to make sure when you have a real-time microservice application to handle these two different types of data at the same speed. Now, how many we're talking about today, or how big your data? Essentially, it's like we're not talking about thousands or millions for transactions. It could be possible to do it. So, but what we're talking about it's kind of like handling 100 terabytes of data, or billions of transactions per second. And these actions are actually quite fast, and you just don't want your application to fail, because failing to receive specific message means like your alerts or trends also might be off as well. So hopefully now you can understand that in this type of application, there are quite few challenges. And these challenges essentially becomes, if you want to connect it to your output or to the application you write, you want to kind of like finding the needle between this amount of data. Obviously, manual analysis is painful. So if I ask you now to go back, for example, and write me an application to, analyze your logs files, you can see how hard it is to write this type of application. And imagine if you want to add scaling on top of it. So scaling becomes really bottleneck. And what we were trying to do is looking at this vast amount of data and finding some kind of alert or usage, for example. Usually, it's like you want to process the data, but processing data is just part of it, whereas the end use case is kind of like providing some real-time analytics on top of it. So alerts means like, how you have specific message, you have specific warning you want to have on your application, or even to define trend, how your application is performing when you run it. Now, obviously, with this type of applications, there are so many tools you can choose from. So this is just to describe what tools you need and essentially which platform you can use. This figure is split into 12 sections, as you can see. So we have 3 rows and 4 columns on it. So it could be open source, or it could be managed service, or it could be hybrid in between. And it depends what you want to do with your microservice application. So for example, do you just want to capture your data? Or do you want to do some kind of data transport? Maybe you do want to do some kind of operation transform, or even like the analytics type of it. Today we'll be focusing on first row, third column. So because this is where things start to make sense if you want to process data in real time at scale. And essentially you can see tools can overlap at some point. So the question becomes here, if you want to develop a real-time microservice application, do you really need to use, 10 tools or 2 tools or 10 tools for this type of applications? Or even how you can manage maintenance for this. So to make it easier, what we can distinguish for this type of application is 2 different areas. So on one side, we have the stream processing capabilities to handle data in real time or to process data in real time. And we also have the fast data storage. So the fast data storage allows you to kind of access your data, historical data stored somewhere, and essentially you load it into memory. And you need some kind of combination between these 2 types, because you want to get, if you remember from previous slide, you want to capture the data in real time, but also you want to have historical data to provide some context. And this is where things start to make sense. So I work for a company called Hazelcast. And Hazelcast is a real-time stream processing platform. It's open source, so, which means basically everything I'm talking about today, you should be able to finish this talk and go back, download the jar file, and essentially run exactly my demo. So this is the open source platform. From one side, you see the sources, so where your data is coming from. So it could be coming from, Apache Pulsar or Apache Kafka. Could be coming from messaging queue or IoT devices, and also could be coming from enterprise application, like this is the way we're talking about today for traces, or it could be coming from database events. Keep in mind, for this type of applications, you don't have only one resource only. You always have more than one. And your job as a developer is to make sure to handle data sources at the same time. So you need to handle multiple data sources at the same time. So once you ingest your data into the platform, so you have 2 options here. So the first option is to do the stream processing capabilities, so what we were talking about today. So maybe you do want to do some kind of data transformation on your data, or you may want to combine multiple sources, or even you want to do some kind of machine learning inference. But at the same time, this is not enough. So why is this not enough? Because it doesn't give you the full picture. So now if I tell you I'm handling my data now, and essentially I received in last window, 100 messages of warning. Does it give you the full picture? Do you know exactly what's happening within the application? The answer is no. You always need to go back, check what happens, for example, last week. What type of data you had in the same scenario. So, and even these type of warning messages might be related to different microservices, not your microservices. So what you want is to get this data loaded into memory, and that's what we mean by fast data management or fast data store. So once you have these 2 different types of data, now It's your job, basically, to connect it to your application. So it doesn't matter which programming language you use. I believe real-time stream processing requires to have like multiple experience in different languages, and we all know how hard it is to learn a new language. And if you're a data scientist, you're coming from machine learning background, you might not have a preference for programming language. You might prefer to use SQL to do it. So you can actually plug it on top of exactly what the platform allows you to do. So you don't need basically to write a Java code for it. So this is a possibility to do it. Now, once you process the data, there are a couple of options. Usually, in most cases, your application sends this type of results or output to end users. So this is alerts or trends, for example. But what we're talking about today, because we're talking about microservices, you want your output also to be sent to a different microservice. So how can you do it? Or maybe you want to send it to a different Kafka topic, and so on. Now, I mentioned scaling. So for most people, when I mention you hear scaling, you assume it's either on compute or on data. And the fact is, you want to handle scaling at two different levels. So you want to handle your data first at compute, and at the same time, you want to handle it at the data level. Keep in mind, when you do scaling for these type of applications, you want to make sure to store your data as close as possible to your compute. Why do you need to do it this way? Why you care about where you store your data and where your compute is? Because we're trying to minimize latency. So for real-time applications, if you have, for example, SLAs of 40 milliseconds or 50 milliseconds, you want to minimize latency as much as possible. And that's why we want, in this case, to make sure we store the data as close as possible to your compute. Now, when it comes to microservices, this is just an example how you can achieve it. Obviously, if you have your data coming from Kafka topic A, and this is your source, could be multiple sources, it doesn't matter at this stage. What you want is to have the option to allow different microservices. So if you have a Java application, for example, you might have microservices in place written in different programming languages. So it could be related, I don't know, in Python. So for example, in this case, what you want is the ability to connect different microservices written in different programming languages into one platform. And this is exactly what we're talking about today. And the output could be related to a different microservice or a different Kafka topic. Now, the question becomes here, why you want a microservice architecture for these type of applications? Why you can't write, for example, a standalone application, similar application? Simply because it's easier to build and enhance. So if you have, for example, a application with 9 or 10 tasks, you want to make sure you split these tasks and it becomes easier to build. Also, it becomes easier to deploy. Remember from previous slide when I mentioned scaling? So you want your microservices to be stored as close as possible to data sources. Obviously, it becomes easier to maintain. So if you store different microservices on different nodes, it becomes easier to switch these nodes on and off. And also, it becomes easier also to simplify the cross-team coordination. So you have one team writing one microservice and different team writing another microservice. Also, it's easier to track performance and scaling, so you know exactly how each microservice is doing. And this is exactly important for real-time stream processing because, as I mentioned, you want to minimize latency. Now, just to go one step back, so those who don't know microservices or not familiar with microservices, essentially what it is kind of like a architecture which allows you to split your application into smaller tasks. And this kind of like leads us to having, instead of having a gigantic application, to have like small microservices or small tasks. Benefits of using this is something called a DAG architecture, which you see it on the screen here. And if you split your application into multiple or different microservices, it allows you to reuse these microservices for different tasks. So for example, if you have data source, and this data source, if you want to create some kind of visualization, you need to read into your application. And if you have some input processing, you want to make sure to store it back in your database. And then if you want to visualize the results and so on. What we're saying here is that when you want to create a microservice application, you want to make sure to split this process into smaller functions or smaller tasks, and from there you can actually reuse these tasks. So for example, if you have some kind of reading function or reading task or reading microservice, you can use it to do some kind of visualization, or for example, or use it for a different service for processing and so on. Now for real time, you can see here if you have multiple topics, you can allow your microservices to handle different topics at the same time. So this is very important to understand. So if you have topic 0, you can connect it to microservice 1. If you have topic 1, you can connect it to microservice 0 or 1 at the same time. So it depends where you want. You have your input and output. And essentially, it becomes really complex, right? So it's not like, as you see it here just on the screen. So it could be microservice 1 is connected to topic 1 and topic 2 and topic 3 at the same time. And just to add one layer of complexity for this type of applications, we want to make sure to also at the same time not to process the real-time events, but also to process the historical events. And this is kind of like what you want to have in memory grid or fast data store. Now, if you're writing a complex application and you want to have multiple data sources, you also want to process it in a microservice architecture. So let's just dive in for this architecture quickly. So from here, you can see we have a Kafka or Apache Pulsar, doesn't matter. And you can have multiple topics at the same time. And you can ingest data into different microservices, or could be related to machine learning, for example. Each microservice is responsible about a specific model, for example. And here you can see you need to do some kind of transformation for your data. And then the ingestion could be related to one or more from these microservices. And obviously, it is like one to many, right? So you see it from one side, your input is one to many, but at the same time, your output or your delivery is also out to, so it's one to many. So essentially what you're trying to do here is to create architecture for many-to-many relationship. Now, sometimes for microservice application, you want to combine scores or you want to combine the output from different microservices. So if you remember, or if you look at this screen here, you see that delivery 1 and N or 2 are not related or are not connected. So this is fine if you have multiple outputs, but in some cases you want to combine these multiple outputs. So multiple outputs means you essentially want to move from one microservice, as you see it on top of the screen, to N microservice or N algorithms. And you want to create the composite score. So you have N microservice, and you want to combine the output from this N microservice. And it depends on where you get your data, obviously. And essentially, if you have multiple data sources, for example, in fraud detection, if you want to write a microservice application for fraud detection, you usually have multiple input. And these multiple inputs could be related to historical transactions. So this is one microservice, for example, or could be related to, I don't know, GPS coordinates. So this can be handled in different microservice, or it could be related to IoT device, for example, or weather data, for example. So you see, in this case, you have multiple inputs, and you want to have multiple microservices, but the output should be combination between all these microservices. So if you want to do it, for example, you want to detect a if an activity is fraudulent or not. So you want to kind of like combine composite score between multiple microservices. Now, we have done a study to see how can you scale this type of application. So we managed to run 1 billion transaction per second on 99% accuracy with just 30 milliseconds latency. And the cool thing about it is the linear scaling, and this was just on 45 nodes. So you can see you just need to add more nodes if you have more data. Now, I just want to show you how you can deploy it. So everything I mentioned today or up to this point is like how you can develop it. But when it comes to deployment, we just need to make sure that you have infrastructure to deploy this type of application. So you can see here we have, for example, one application. So this application could have multiple microservices in it. So you have the Kafka topic, and from there you have also exactly what we discussed. So you have some kind of real-time data, and at the same time you have some kind of microservices written in Python, for example, or Java. And you do some kind of processing on this data, and you do visualizing. Now, if you want, I'm just saying it's slow Python code, but it's just like to compare it to when you want to deploy it. So if you have a Java environment, to deploy it, if you want to actually add more microservices or more models or more algorithms, you can actually just plug these models into your platform. And if you want to scale it, you can add more clusters, obviously, or more nodes to your system. And you need to have this configured in your configuration to allow auto-scaling to scale up or down. You can have it stored locally on your machine, for example. You can, or wherever you want to do it. So in this case, you can see on the host, so for example, for today's demo, or you can have it on the sidecar. So this is as close as possible to your node. So this is important if you want to avoid latency, or you can simply create some kind of some kind of farm. So essentially, farm is a container where you can store these models, and from there you can actually connect it to different nodes or different pods in your architecture. Now, for the demo, what I wanted is to show you how you can apply these concepts. So you should be able to do it exactly after we finish. So whether you want to download the jar file, so this is essentially you can deploy it locally, or if you want to run it on the cloud. So running it on the cloud is important because you want this type of application. Remember, this type of application require low latency. So if you want to have data coming from multiple machines, you want to store these as close as possible. So one way to do it is something called Hazelcast Viridian. So this is serverless service, which means essentially you can, repeat exactly. So you don't need to download the jar file. You can run the platform on the cloud. And the application itself will have a mechanism to analyze logs in real time. So each application you write has some kind of logging mechanism attached to it. And we have two options for it. So the first option is to provide some kind of alerts. So these alerts kind of like providing warning messages, for example, or could be the option two is to provide the trend. Now, how do you write it? How do you create this logging mechanism? So we're going to use something called map structure. So the map structure allows us to send log messages to the cloud as key value pairs. So the key in this case is relevant to the IP address, for example, port or application ID. So this kind of like give you our timestamp. So this value is unique. And then you have the value for this map. So the value, you can structure it the way you want. So it could be message for the log or could be related to level, so whether it's information, warning, or error, for example, or even, for example, if you want to do some kind of natural language processing on top of your messages. So, which means basically you read the actual text for each message and you try to make, I don't know, maybe find a sentiment for it, if it is positive or negative. So once you have this structure, what you want is to load it into map, and this one will provide the alerts. So from here, you can see I'm using JSON format. You can have the option to store it in a string format, string or varchar, usually faster if you care more about latency. But if you want to do more analytics, maybe you use JSON format. Becomes easier to parse the actual, contents from the message. So here you can see the port where it's coming from, timestamp, level, what type of message, maybe thread and logger as well. The actual code I will show you, but let me explain it first. So what we're saying here is you need a client to connect to the cloud, obviously. So the client, essentially, you need to download, depends on your programming language preference, so whether it's a Java or Python, or even the SQL, for example. And this values, the key value pairs, can be stored in this structure. So this is just SQL, so allows you to manage the queries in real time. So on the left, you see your keys, which are the IP address timestamp attached to it. And then you see the values on the right side, where you store some kind of level as well as a score. The score itself that you can set, for example, you can choose it for a value to be from, I don't know, from 0 to 100, and then you apply threshold on top of it. So you say, for example, if it is above 90, provide me with some type of alerts. Now, the option 2 is to create trend out of your log messages. So the trend are usually preferred to look at previous log messages, and you can specify window on it. So you can say, for example, I want my window to be to move forward every 10 messages or every 1 message, but in window size of 10 or 100. It doesn't matter. You can adjust it in your application. What is important here is to take your keys for your map, and the keys are essentially just where your log messages are coming from and the timestamp attached to it. Once you have your input, you need to load it into the platform. And in this case, the platform allows you to create 2 maps. So the first map is the trend map. So trends is just essentially just normal. A mathematical model, it could be machine learning model. So in my case, I'm using linear regression to do it. Could be, to be honest, any model you want to create. It reads the data, and from this data, it creates trend based on previous values. And of course, the threshold you want to apply to it. And you need a different structure at the same time. So the trend is just to allow you to see how your application is performing in real time based on log messages. And prediction will actually allow you to take the trend and check if the next message will be maybe, for example, an error message, or maybe you're running out of memory as a use case. So something to, give you some kind of warning on top of it. So the goal from this type of applications is to provide a real-time analytics. So what you see there on the right side is kind of like the output. So we're looking at values either 1 or 0. And again, it doesn't matter how you want to format it. So in case of 1, provide me with alerts, otherwise don't. So if it is a 0. Just to give you the idea of the architecture here. So we are reading from multiple sources for this type of application to create multiple microservices. And the microservices allows you, in this case, first to actually add timestamp. So this kind of line, we're trying to do some kind of for data transformation, calculate the trend and then group it by the transaction or group it by the machine if you want, and then create the trend map. And from there, we can use the trend map, which is like normal map in memory, to kind of provide some kind of prediction. So this is the prediction map. And from the prediction map, you can provide some kind of output. So the output in this case could be, you send it to file system, and then you can have a monitor on your file, or maybe you can send it to Kafka topic, or maybe some kind of, I don't know, end users web application through WebSockets, or even the SQL browser. Now, for the code, for the second option here, we look at score probability. So we're using something called map using a service. And from here, first step is just to define the trend based on the values we're reading and using a linear regression model. And from there, we say, check the next message based on the trend value. Obviously, if it's not stored, you take it, as you store it, and then you read it, and you check if it's above 100 or above a threshold. Provide alerts or set the value to 1. Otherwise, set it to 0. And the output, you will see in this case, if you have multiple transactions, and for each transaction you have different log messages. So this is one way to do it. Obviously, you can have the option to do it in different ways. So you can see values of 1. This is where areas you provide alerts. Again, alerts mean different things. Or otherwise, don't send the alert. Now, from this point, there are 3 ways to proceed, right? So you can use the SQL. You can say, for example, I want to create a job. So this is the actual process to read from map and then sync it to a different map, or read from, again, different maps. So you define your source. So the first 2 options are batch mode, which means not real time. We're talking about the third option here. So the third option allows you to read from something called map journal, which is essentially exactly what we're talking about today, is the different in events in real time. And the real time, we mean even before you store it into your database. You check the values for each, you can go through the text, for example, and check the value. So let me just move quickly. I just wanted to show you how you can connect it to the cloud here. If I can. So this is 2 options here. So the first option, if you want to download the jar file, right, all you need to do is to add Hazelcast into your POM file. And from there, you should be able to actually run exact code. And from here, this is the second option, if you remember. So the second option, exactly, I just say I want to build a pipeline. You can read it from CSV file, or you can read it from Kafka. And you define instance, depends how many instances of Hazelcast you want, and then you can create the job. In my case, building the pipeline will have a map journal. So this is the third option we talked about, and to check specific value. And from there, you can basically create the linear regression model and provide some kind of alerts. So you can send the alerts different ways. So for example, you can send it to a different map here. You can send it to JSON, or you can send it to WebSocket. The other option is to use the cloud, and this is important if you want to handle data in the real time. So the cloud essentially allows you to exactly describe, or sorry, do what we talk about on the cloud. So you log into the cloud, and from there you can connect your client depending on which programming language you want to use. So you can use Java client, a Node client, or Python, for example, or .NET. Or even if you don't want to use any client, you can still use the management center, which I will show you now. This client Once you download it, you can connect it to the server, to the cloud, to Hazelcast serverless. And from here, you have the management center. So this will allow you to do the management. So from here, you can see how many clients you have within the system, how many members. You can see the storage in real time. You can see the maps, for example. You can check the cache, or even if for streaming, you can check jobs. For example, how many jobs are running or completed or failed. Or even you can do some kind of SQL queries. So this is just normal map, for example. And if I run my application here, so it will connect to the Hazelcast Viridian. And this process is just simply to create some values and store it into map. Obviously, this is exactly if you want to create the log messages, you can do the same thing. You can specify the key and value, and you create the job. And if I go to actual management center using the SQL browser, from here you can see I have the option to query the data. And if you're doing streaming SQL, you can actually track these changes in real time. And from there, just to summarize before we go back to, before we answer questions here. So to summarize, for writing a microservice application, this is what I want to do here. So first of all, you need your log messages, or if you use microservice application in different contexts, you want to store it somewhere in a platform which allows you to do real-time stream processing. This platform should allow you to do two different activities. First activity is to read data in real time. And second activity is to actually provide some kind of historical data. These two different types of data should happen in the same time. So if you, for example, using Hazelcast to do it, you can do exactly what we talked about. If you don't use Hazelcast, you probably end up with using multiple solutions. And for log messages or for microservice applications, usually you need to store it on the cloud. Because you have multiple machines and you want to minimize latency. You have multiple options for format. For example, you can use JSON if you want to do some parsing. If you're interested in speed and low latency, you can opt in for varchar or string, for example. And you want to have some kind of map structure. So in my case, I'm using IMAP to allow random access to handle or check data, because you want to have some kind of rebalancing between different types of data. And also remember, you want to have some kind of eviction policy in place, because obviously you have some kind of limitations on your map. And because we're talking about logs usually have some kind of sensitive data. So you want to just to consider security for this type of cases. So as mentioned, we have a large and active community for Hazelcast. So if you're interested in this type of solutions for real-time stream processing, we have a Slack community channel for answering all the questions. We do also Twitch streams just to go through some kind of demos and tutorials how to do real-time stream processing. With that being said, I think that's pretty much what I wanted to cover. So thanks very much for listening. And if you have any question, I'm open for questions. Otherwise, I will stay outside to answer any question. So thanks very much. Thank you. So questions. I think we have a platform for this one here. Let me just check. Do I need to refresh? Okay, so no questions. So any question regarding the presentation here? Right. So the question is, can you compare Apache Ignite, Kafka, and Hazelcast? Yes. So, I mean, you need to think about your data. So first of all, what is the task you're trying to do with your data, right? So this is the important point to start your process. So if you have Kafka data, for example, or Kafka topic, you just want to stream processing, to do some kind of stream processing, or to process events, that's fine. So Kafka is enough. But if you want, for example, to provide some kind of, I don't know, some kind of contextual data, you want to understand your data coming from Kafka, you probably need to use something else on top of Kafka. So the idea of using Hazelcast on top of Kafka is to give you this advantage. So you want to take your process a step further. So you take it from stream processing to real-time stream processing with the contextual data. Kafka doesn't give you this option, so which means basically if you want to, I don't know, to check your data stored somewhere, you probably need to use different tool as well as Kafka. In Hazelcast, you can read your data from Kafka, and once you read it from Kafka, you can actually access data stored anywhere on the file system. And this is the advantage here. So you get the contextual performance, or you get the context out of the data. So hopefully this answers the question. So if you're not using Cloud Hazelcast, can you send your trends metrics? Yes, to provide some charts. So the answer is yes. As I mentioned, we have multiple syncs, which means basically you can send it to wherever you want. So you can you can send it to Kafka topic, for example, and from there you can do some kind of visualization. You can send it to WebSocket, or even you can store it in file system and you do some kind of visualization. So yes, it is possible. All right, thank you. I'll stay outside. If you still have any questions, come and grab it. Thank you.